So let's remind ourselves where we stand, what we were doing before break a week ago. We were working on 1D transient problems, and we had gone through, remember we did Laplace, we did separation of variables. We started doing numerical solutions, and we went through and got to the point of deriving the equations for the numerical 1D transient problems. So just remember what we're doing, right? We have here an example of a fin, and the fin is 1D, right? It has just one temperature gradient in the x direction. And we're trying to model that temperature gradient with our set of equations here. So we discretize the domain in the direction in which the temperature gradient exists, which is x, and we have n nodes there, one on both boundaries as well. So you have those n nodes, and then we just go through and do the energy balance. So we draw our control volume around a single node. This is the ith node. And we have stuff going in from the left and the right, and those would be negative if they're actually leaving in reality, but just draw them all going in. And then we have something from the surroundings as well. So that is exactly the same as what we did last non-transient problems last time. What we're adding now is this dUdt term. So what makes this problem different is that we have to go through with our energy balance, including dUdt, and we end up with an expression that includes temperatures at each node, and it includes the derivative of temperature at node I with respect to time. This, when solved for dT/dt, becomes a state equation. And the state equations help us step forward in time. Right, so that's what we're doing. We went through this, deriving these equations last time. So we'll skip back ahead to where we left off. So we have our implementation here for the Euler method. One thing I want to circle back to, the first thing I want to circle back to is this idea of the critical time step. We went through, and if you remember what I said, for the critical time step in explicit methods, this is only for explicit methods, you need to have the term that's multiplying the temperature Ti be positive. So that is maintained when the time step is less than the critical time step, which you just solve for the equation where it's positive, and this becomes your expression for critical time step. So again, this is for explicit methods only. If you're doing implicit is always stable, right? So there is no critical time step for implicit methods because we're using the derivative at the end of the time step. For explicit methods, that's not the case, so we need to solve for the critical time step. But I want to think a little bit about what this critical time step is telling us. So it turns out that when we're taking the critical time step, what we're really doing is computing something like the time constant of the control volume for a single node. So let's go through this derivation to compute the time constant, and you'll see kind of how it works out. So let's say we have some node, and we have heat transfer coming in these three directions, where we have our from the left, from the right, from the bottom. So if you remember what the critical time step computation is trying to tell us, that is, so we'd say the time constant for this node would be tau, which is equal to our surroundings times the heat capacitance of the object, right? This is the lump capacitance time constant, tau LC. What is the resistance to the surroundings for this node? Right? It's, well, this, for the convection part, but for this node, it's actually the conduction as well. So you have basically three paths that heat can take to go to its surroundings. So we would write this as tau LC is equal to the three different parallel paths. So you'd have 1 over our conduction plus 1 over our conduction plus 1 over our convection to the minus 1 power. That's our equivalent resistance to the surroundings. And then we multiply that by the heat capacity of the object, which would be C. Actually, let's just write that out. It is what? The volume, which is going to be delta X times AC times rho times C. Right? Delta x times AC is the volume of this node. So that computation, tau LC, gives us the amount of time that this volume is going to take to respond to a change in its surroundings. And again, the surroundings can be conduction or convection. So let's go through and write out what this becomes, and you'll see where we're going with this. So tau LC, if we actually evaluate these resistances, it becomes 2K AC over delta X. That's our two conduction resistances combined together. And then we have the convection resistance, which is going to be H bar times perimeter times delta X. All that to the minus 1 power. Again, times delta X, AC, rho C. Right, so we're going to go through and simplify this out. So tau LC becomes delta X AC rho C divided by, we're just putting this thing in a denominator, 2K AC over delta X plus H bar perimeter delta X. So what we can note that the AC is going to cancel out of these terms, does not cancel out here, but we can just kind of divide out. What else? The delta X is going to cancel out of that term. So we can simplify this down a little bit. If we do that, it becomes the following. Tau LC is equal to 1 over 2K AC over delta X squared AC rho C plus H bar perimeter times delta X over delta X AC rho C. Okay, so that's just dividing through by the numerator. Now we can simplify it down, and this becomes tau LC finally is equal to 1 over 2 times, well, K over rho C is alpha. So it's 2 times alpha over delta X squared plus H bar times perimeter over AC rho C. Oops. Okay. So if you follow all that and look at this and look at that, they're the same thing. Right? This term, or these two equations are the same thing. So it turns out that our critical time step is, in this case, exactly equal to the lump capacitance time constant. And why is that important? Like, what is that telling us? That means if I'm doing a computation and I, let's say, take a time step that's much larger than my lump capacitance time constant, the response associated with that step is going to mostly be, resolved. It's going to kind of go past that initial linear phase of the response and become really nonlinear. And because we're making a model here that's based on resistances, it has to be linear all the time, or it has to be close to linear. When you start getting this really nonlinear response in large multiples of tau LC, then your estimate of a linear problem goes away, and you can be really wrong. It becomes unstable. You're missing your target, right? So by keeping our critical time step to the lump capacitance time constant, we're pretty much just ensuring we're maintaining a linear problem. Okay? Does that make sense? Any questions on that? Okay. Okay, so that's sort of the justification for this. Again, for the third or fourth time, this only applies to explicit techniques. So what you're going to be doing in the homework is computing the lump capacitance time constant, or the critical time step. For your problem, I'm asking you to use Hoynes technique. So that's still explicit, but you need to, it's a little bit tricky to evaluate Hoynes technique critical time step, so I just ask you to do Euler's method critical time step and just report that. Okay, so don't be too confused on the homework. Just go through and do the Euler's method critical time step and report that value rather than the Hoynes method. Okay. So that's, I guess, the basis there. What we're going to do for the rest of today is go through the more advanced techniques again. So if you remember, we had talked through in our 0D problem, transient analysis, we talked through different ways that you can use numerical techniques to predict the temperature as a function of time. So those included things like Hoynes method, Runge-Kutta, the implicit or Crank-Nicholson method, the integral commands in Ease or ODE solvers in MATLAB, or actually Python, right? Old notes, Python. You can use any of these techniques. So you can do that for 0D, you can do it for 1D. So let's go through today, talk through the 1D problems, and see how you actually apply them to this type of a situation. Here's the solution that we came up with, hopefully, where we have our, we've gone through the steps, 1, 2. So we distribute the nodes spatially, carry out the energy balance on each node. That leads to a state equation. Our state equation is dTi dt. So we're going to have, if we have, n nodes in the x direction, we're going to have n estimates of dt dt, one for each node. And then we need to come up with a function that evaluates that. That's our state equation, right? So this is our state equation that we've come up with here for the first node, for the ith node, and then for the nth node. We have this ability to evaluate the derivative with respect to time. Now we need to plug that into these different techniques. All of the complexity or all the advanced techniques are dealing with step 3 here. So step 3 is where we're going to spend our time now. We'll just take this kind of as the same all the time. So one thing you're going to want to do is, as you're going through this, I've said that this dt dt vector, this set of derivative estimates, is something that we're going to want to be able to compute. When you're going through this and you're going to really want to do this for the homework, is go through and create a function that evaluates that vector, dt dt, for every node I, and returns the values that you compute. So you want to be able to call a function, give it some temperature, give it some time, and it will give you back the derivatives. So that way, when you go through and you need to make multiple evaluations of the derivative for, say, RK4 or for Hoynes method, you can do that easily without copy-pasting the code every single time. So I want to just show you how you do that. So let's flip over to Python. And I'll show you how we implement this, this type of function. And first, I'll show you how you solve it with Euler's method. So here we're taking our function. This is the problem that we're dealing with. First, maybe remind yourself what we're doing on the import statements. We need to import NumPy stuff. So we're using that NumPy libraries as NP. And then we're creating our arrays here. So we have all the problem information we need. We're passing in some other information. Here's where we now allocate for our dt dt vector some array or vector of zeros that'll be filled in later of size n. So n is the number of spatial nodes. So what you want to notice about this is I'm not allocating dt dt for space and time, even though we will need to evaluate dt dt at every single time. So what this function is supposed to do is give you the response or give you the derivatives at a specific time. So inside this function, we don't need to worry about time at all, except to know what we're being told that it is. So once you pass in a given time and a given current set of temperatures, right? So t here is a vector, my current set of temperatures for every node. I should be able to go through and calculate dt dt. So here I do that for node 1. This is straight from the slide. Nodes I, and then node n. And again, for this one, you could use that vector notation, right? Instead of using a for loop, you could use that. I just didn't update it that way. But we evaluate every single dt dt and come back, and then we return that vector for whatever function is calling it. Okay, so let's look at an example for Euler's technique of how that works. So I am doing this for 21 spatial nodes. And I want to run Euler's method here. So here I have Euler's method. We had previously gone through and set up Euler's method to say I'm going to step from temperature J to temperature J plus 1. So this is for the first node, this is for the ith node, this is for the nth node. And it's doing that based on the current temperature and then the evaluation of derivative. So what we wanted to do with this function is replace this verbose statement of the derivative with just calling a function. So I'm going to comment this out, and let's look at this instead. So this is now taking my current temperatures at time step j, adding to that my evaluation of the derivative times the time step, dt, and it's taking that and then computing the next temperature, right, Tj plus 1. So by putting this in a function, I mean, for Euler's method, it's sort of not clear how this helps you. But when you get to other methods where you have to evaluate it multiple times, you don't, it saves you all that typing. You'll see that later on Runge-Kutta. So let's see if this actually runs. OK, so here's our plot, right? This should look familiar. This is kind of what we had last time. We have this fin, this line here. I guess I didn't put a legend, so lose a point for that. But you have response at the very base of the fin. So this is where the heat flux is being forced into the base of the fin at x equals 0. So right away, you should see that the temperature ramps up as a function of time. And then as you go further out in position, there's going to be a lag. So way out at the end of the fin, it doesn't actually see that thermal wave until 15 seconds or so, and then it starts kind of ramping up too. So this is the same thing that we had before, but we've just implemented it as a function.